Okay, hi everybody. Welcome to our next meeting of the Dynamics and Number Theory seminar. Felipe, if you are here, maybe you can perform the hosting duties
Happy
this
to.
time and tell us what is going to happen.
Okay, welcome everybody. We have Lei Yang today from Sichuan University speaking on Khintchine's theorem on manifolds. Go ahead.
Thank you.
Thank you very much. Thank you very much for the invitation. It's my pleasure to speak here. This is a joint work with Victor Beresnevich from University of York. It's about Khintchine theorem on manifolds. Okay, so let me briefly recall what the Khintchine theorem says. So given a decreasing function defined on positive integers psi, we call and a dimension n, we call n-dimensional vector x a psi approximable if there are infinite many solutions p over q such that distance between x and the p over q is bounded by psi of q divided by q. So Khintchine theorem says that you can the set of psi approximable points is denoted by Sn of phi, and then Khintchine theorem says that you can use this summation, infinite summation, to determine the size of Sn psi. If the series is convergent, then it is zero measure, and if the series is divergent, then it has full measure. Okay, this is basically the most classical result in Diophantine approximation. So now we're considering the Khintchine theorem for all manifolds. This is a problem asked by Kleinbock and Margulis in 1998 in their famous paper. They ask if we can prove Khintchine theorem for non-degenerate manifold, namely if we consider points on non-degenerate submanifold M, we can use the same summation to determine the size of Sn psi lying on the manifold. So this is a natural question and also very close related to dynamical system, and also it's related to the result of Kleinbock and Margulis proved in their famous paper. In that paper, in the same paper, they proved the following result. If we consider some special approximation function, we consider this psi is just some negative power of q, then this summation criterion holds. Namely, if this tau is greater than 1 over n, then the size is 0. If tau is less or equal to 1 over n, then it's a full measure set. Actually, it's a full set because of the Dirichlet theorem. So this is the so-called Baker's Sprinzuk conjecture, and they proved this conjecture in that paper, and then they ask a final question about Khintchine theorem. And in this paper, they develop some techniques from homogeneous dynamics to study such Diophantine approximation problem. And a very important result is a quantitative non-divergence theorem, which we will talk about later. So for this problem, we have several significant results. For n equals 2, namely the planar curves, it is totally solved by the convergence theory was proved by Vaughan and Vinali in 2006. And the divergence theory was proved by Beresnevich, Dickinson, and Vinali in 2007. It's basically they prove it by counting the rational points near planar curves. Okay, so this is dimension 2, and for higher dimensions, the divergence theory was proved by Beresnevich in 2012. But the convergence theory is a little bit complicated. There are only partial results. Basically, they require the manifold to have some curvature condition, and which implies that the dimension of the submanifold is not too small. Like the dimension of the manifold D is at least some constant times square root of n. N is the dimension of the whole space. And this basically this condition comes from the method. They use the Fourier analytic method, and if you want to control this Fourier series, then you need those conditions. And also there's another result about convergence theory, which also this is the result about convergence theory. They require some curvature condition, which implies that d times d plus 1 is at least 2 times n. It's by Dodson, Ryan, and Vickers in 1991. And then recently, Beresnevich, Vaughan, and Vinali, and Zorin, they prove another result for convergence part. So they require the submanifold to have two non-degenerate condition, which means that the second derivative, the first derivative and the second derivative spans the whole space. That implies the dimension is at least 1 plus n over 2. So basically, for example, for curves in higher dimensions, there's no result for non-degenerate curves. And recently, Huang and Liu proved the convergence theory for affine subspaces with some differential condition on coefficients, also using the Fourier analysis. So this is basically so the convergence theory is basically open for many cases, and our result, my result with Beresnevich is basically about the convergence theory. We can prove the convergence theory for any non-degenerate manifold without any condition on curvature and dimension. In particular, we can prove it for for non-degenerate curves. Okay, so this proves the problem asked by Kleinbock and Margulis. So we use some different approach compared with the previous works. Our approach combines the geometry of numbers and homogeneous dynamics. Previous work basically builds on the analytic number theoretic method, namely the Fourier analysis. Basically they count these rational points near submanifolds using this Fourier analysis analytic method, and using the counting result to estimate the measures. And another final question is about Hausdorff dimension. For example, if we just consider this special approximate approximation function q to the minus tau, if tau is greater than 1 over n, we know that it's a zero measure. And further, we know the Hausdorff dimension of this Sn tau is n plus 1 over tau plus 1. This is a classical result of Yannick. And the natural question is, can we determine the Hausdorff dimension of Sn tau lying on a non-degenerate manifold? So by the result of by Kleinbock and Margulis theorem, this set has the zero measure. So it's natural to consider it's a Hausdorff dimension. Okay, so the conjecture is that the Hausdorff dimension is n plus 1 over tau plus 1 minus n minus d, if tau is not very large, like between 1 over n and 1 minus d, 1 over n and 1 over n minus d. So d is the dimension of the manifold. Okay, so so for n equals 2, the conjecture is proved by the previous mentioned works. The upper bound is given by the convergence theory paper basically gives the upper bound of the Hausdorff dimension, and the divergence theory paper gives the lower bound. So that's basically again about counting rational points, because on planar curves they have a very nice error term for the counting, so they can calculate the exact value of the Hausdorff dimension. So for n for higher dimensions, the lower bound is proved in the previous mentioned paper by Beresnevich. So the open part is the upper bound of the Hausdorff dimension. Actually, the upper bound is open for most cases. There is a partial result by Jinjun Huang quite recently. He proved the hypersurface case, namely the codimension 1 case with some curvature condition. Again, the Jing Huang's method is also based on counting rational points and also based on the Fourier analysis. So our approach can prove a little bit, can make a little bit progress on this problem. We can prove that for tau is between 1 over n and 1 over n plus a small number, this conjecture is true. And for curves, we can get a slightly better range for tau. For tau is between 1 over n and 1 over n plus 1 over a times n cubed. This conjecture is true. So related to this Hausdorff dimension, there is another question called the spectral problem. I think asked by Bourdieu. In this question, we consider the spectrum of X. So lambda n of X is the maximum, the supermum of tau, such that this x squared x to the nth power is inside the Sn of tau. Then there's a conjecture by Bourdieu and Lauren in 2007. They conjecture that this spectrum can take any value between 1 over n and positive infinity. So the conjecture is proved for n equal to 1 and 2. For 1, I think you can use a continuous fraction to prove that. For n equals 2, you can use the previous mentioned result. Because for planar curve, if you have a nice counting result, then you are able to prove this result. Okay, so for higher n, Baziahin and Bourdieu recently proved that if for lambda is slightly larger than 1/3, it's true. So the open part is does this spectrum contain from 1 over n to this 1/3 plus 4 over 3n. So our result can prove that this spectrum contains a small interval from 1 over n to 1 over n plus 1 over 8n cubed. So we can make a slight progress on this problem. Okay. So this is about our result, and next I want to talk a little bit about how we translate this problem to a homogeneous dynamics problem. So we consider this canonical homogeneous space SL n plus 1 R divided by its integer points. Then every point on this homogeneous space can be identified with unimodular lattice in Rm+1. And this nice property is the basis of Dani's correspondence. And this homogeneous space is it's not compact, but there is a nice criterion, Marlowe's criterion, to describe the compact subset. Every compact subset is contained in some k epsilon, where k epsilon is the set of lattice without any non-zero vector shorter than epsilon. Okay. So the dynamical system we are considering is so the base point we're considering is the upper triangular this unipotent matrix. We put this vector. So given a vector x, we can define an upper triangular matrix using this formula. And then we consider the diagonal flow of on this space. This diagonal flow is a little bit complicated than usual, but just for some technical reason. So you can just assume it's some usual diagonal flow. So now from psi of Q, we define another quantity called phi of t. Phi of t is defined in this way: psi of e to the t times to the nth power times e to the t, and then take 1 over n plus 1's power. And we will use this phi of t in the calculation. Then we consider that to simplify the explanation, I just focused on the curve case. So I just fixed a non-degenerate curve phi. So then we can embed phi into this in the place of x, and then we get a curve inside the homogeneous space. So u of phi is a curve, non-degenerate, some curve in the homogeneous space. Then we consider this shrinking target redoubt problem. So for t, we consider the push forward of the curve by a of t, and then we consider the set of points outside this expanding compact subset, which means inside a shrinking neighborhood of infinity. So this is a shrinking target redoubt problem, and by some standard argument or by Dani's correspondence, we can translate this psi approximable point to this lim subset of this shrinking target problem. The point phi of x is inside Sn of phi, if and only if this X is inside the lim subset of this BT phi. Then we just want to show that if the series is convergent, then the lim subset is zero, has zero measure. So to prove lim subset is a non-set, just to use the Borel-Cantelli lemma, the convergence part of the Borel-Cantelli lemma. So it suffices to show that the sum of the measure BT's psi is convergent. Okay. So the key point is to estimate the size of BT phi, which is the proportion of the points outside inside the shrinking neighborhood of infinity after translation by this AT. As I mentioned before, this summation for psi of Q is convergent is equivalent to the condition that the summation of this phi to the n+1's power of t from 1 to infinity is convergent. So by considering the summation for psi is equivalent to consider the summation for phi.
Excuse me, like, can you show again how psi is related to phi? It was okay. Previous slide or something.
Yeah, this.
Okay. Sure. So you have too many phi's. One phi is.
Yeah. Sorry about that. This is a different phi.
Different phi. Okay.
And another factor is that the measure, the volume of or the hard measure of this shrinking neighborhood is more or less phi to the n+1's power. So if this proportion is also more or less this psi to the n+1's power, namely if the proportion is more or less the volume of the shrinking neighborhood, then we're in good shape. But this, for example, if we can prove this push forward of the curve is effectively equidistributed, then with some small error term, then we can prove this. But that's I think that's the harder, that's a more difficult problem. But this gives us a hope that this can be this is true. So let's have a look at the famous quantitative non-divergence theorem by Kleinbock and Margulis. This theorem says that if we consider the push forward of this curve and consider this the proportion is inside proportion of the point lying inside this small neighborhood of infinity, this measure is less or equal to epsilon. If this neighborhood is the complement of k epsilon, then the measure is less or equal to c times epsilon to the alpha's power. So the problem is this alpha is usually very small compared with the expected, compared with the volume of this the volume of this neighborhood. The volume, if we consider the complement of k epsilon, then the volume is epsilon to the n+1's power. But usually this alpha is more or less 1 over n+1. So it's much smaller than the volume of this neighborhood. So that's the main reason why this this result, this famous result, this important quantitative result can work for this special quantitative, the special approximation function, but not for general approximation function like this, 1 over q to the 1 over n times log q. So let me do some simple calculation. So if we have this approximation function, then the corresponding psi of t will be q to the e to the minus tau n tau times e to the tau n t times e to the t, and then take 1 over n+1. If tau is greater than, here tau is greater than 1 over n, then this is some minus power, say eta times t. So this is the corresponding psi of t. So then somehow if we have this quantitative non-divergence, we can get the measure is bounded by this phi alpha's power of phi of t, which is e to the minus alpha eta t. So if eta is positive, then this summation is always convergent for any alpha, for any positive alpha. So this one is always convergent. But if you look at this summation, this approximation function, let me erase something. So if you use this approximation function, the corresponding psi of t will be this will be e to the 1 over nt times t to the nth power times e to the t, and take 1 over n+1. So So in this case, this guy is equal to t to the 1 over t to the n over n plus 1. Okay. So the summation for the volume is sigma psi of n plus 1 of t. Then this is 1 over t to the nth power. This is convergent. But if you use this approximation, this estimate, you will only get psi to the alpha's power. This one is let me write it here. This one is summation of 1 over t to the m over n plus 1 times alpha, but this alpha is very small, so this one will become divergent. So this will not be able to prove the measure is 0 using this estimate. That's the reason is this series is very sensitive to the power, but this geometric series is not. Okay, so this is so in the paper we basically the main result is the following dynamical version of quantitative non-divergence or a stronger version of the quantitative non-divergence. It means that the estimate of the proportion can be divided by 2 parts. The first part is we call the main term is the comparable with the volume of the shrinking neighborhood. And there's another term called the arrow term, but the arrow term is exponentially small for with respect to the t, the time. So using this quantitative, using this dynamical version of quantitative non-divergence, we are able to get this. We are able to get the convergence of the this part. Actually, this measure is just this the measure for b of t phi. Okay, so b of t phi has 2 terms in our result. Can be bounded by the first main part is the volume, and we are given that the volume summation is convergent. So the volume part is the main term is convergent, and the arrow term is exponentially small, which means which is also convergent. So then we are able to prove this summation is convergent. Then by the Beresnevich lemma, we can prove the limb soup has 0 measure. So this is the key point of the proof. Okay, so then let me just explain the idea of the estimate in a very brief way. So the main idea is we divide this curve into 2 parts. For different for every t, we divide it into 2 parts. The first part is called major arc. The second the rest of it is called the minor arc. We just borrow the name from the circle method. And then for the major arc, we use this geometry of numbers and combined with some dynamical ideas to count the rational point. And then this part we can get this desired upper bound for this rational point, for the number of rational points. That gives and the number of rational points will give the proportion of this measure, the measure in the major arc. So the major arc gives this main term, this term is epsilon to the n+1. So this is exactly comparable with the volume of the neighborhood. And for the rest of it, for the minor arc, usually we get some very special property of that for the minor arc. And then that allows us to use quantitative non-divergent result. But we need to use another version by Bernick, Kleinbock, and Margulis. And using that quantitative non-divergence theorem, we are able to prove that the minor arc, the measure of the minor arc is exponentially small. This gives the e to the minus eta t part. So, and then if we combine them, we will get this dynamical version of quantitative non-divergence. That's it. Thank you very much.
Well, why don't we first thank our speaker? And are there any questions or comments?
I had a question, hopefully. Does the results on the divergence theorems imply like sort of a lower bound in this sort of modified version of your quantitative non-divergence?
Lower bound.
If the curve
yeah,
was,
of course, yeah.
So if the curve was effectively equidistributed, you would expect like somehow these measures to be asymptotic to epsilon to the n+1 with this kind of a
of course, yeah.
Yeah, that's a good point, maybe.
Okay, because then somehow this your result and the previous results somehow give like a complete picture, at least near the cusp, as if you had effective equidistribution. Somehow it would be.
But this we can get somehow the approximately how many the measure approximately the measure inside that the neighborhood.
Okay, thanks.
Other questions?
So let me try to ask a question. So basically, do you understand in which places of the proof you are using monotonicity of psi? Because I know many people in the audience are spending years fighting this condition. So I know for the correspondence, for us it was important to have
the factor 1 use the decreasing of of psi.
Yes, so when the correspondence is set up, yes, okay.
Yeah.
So you don't know what happens if you remove the assumption.
Yeah, we don't know.
Yeah, otherwise, I like this new quantitative theorem a lot. So so can you can you derive a version for any Gmod gamma? Presumably just saying something about the cusp in terms of
right,
injectivity
that's
radius.
yeah, that's a little bit different.
Yeah, well,
Yeah, because
probably
we
in
use
the arithmetic
geometry.
case, you can maybe infer something from lattices.
Yeah, but yeah, that's quite different because we use this counting. We count the rational points near this manifold, and for general case, we don't know if there's any geometry of numbers we can use or counting something.
Dmitry, of course you can do some, right? So your paper with Margulis and Bernick does exactly this for the dual case.
Yeah, that's another
Right.
comment, and in the dual case, somehow it is better.
Yeah, it's done differently, I know, but all I mean is presumably you can get some results, but if you're asking about a general result, that's probably some way off.
Mm-hmm. Yeah, I see. Actually, maybe another question, since I'm asking questions. What happens if you add well, if you stretch in different with different factors in different directions? So, is there a weighted version for curves?
You mean weighted case of this a simultaneous approximation?
Yes.
Well,
and also weighted case of this new non-divergence result. Is it important to have so for at least for in the original theorem it was not important, right?
So
we had this multiplicative case, but in this in your new non-divergence theorem, can you put arbitrary diagonal group?
We haven't written down the theorem, but we hope to prove a similar result.
Mm-hmm. That's interesting. Okay, thanks. Very good talk, by the way.
Thank you.
Are there other questions or comments? Well, maybe we can thank the speaker again and conclude the formal part of the talk. Thank you, Lei.
Thank you very much.
So probably it means that I should push the stop recording button since the formal one is over. So again, thank you everybody, and look forward to seeing you next week.